Welcome to the 2026 Lymon C Reese Distinguished Lecture. For me, it's such a privilege to welcome you to campus, to our geotechnical group. Today, this welcome comes from my very critical geotechnical faculty. And here you have Dr. Clara Saracho. Where's Clara Saracho? Dr. Shadi El Motar, Dr. Bob Gilbert, Dr. Krishna Kumar, Dr. Ellen Radji, Dr. Ken Stokey, and myself. So for me, it's such a privilege to work with you guys, and thank you for being who you are. So thank you for being here with the entire geotechnical faculty. Who is in the audience? Let me see. Generally, we do have a good contingent from Texas A&M. Very good. Thank you for being here. What about from Texas State? There you go. And I would like to highlight the last kid in the block, which is our group of the GI chapter in Austin. Where are the officers of the GI chapter? There you go. Thank you for being here. And we all need to support you. So thank you for the hard work in making it happen. All right. So just as a brief overview, I didn't mention our very important GI chapter of our very own UT Austin. And here just to show you what you would get if you are here, and this is just 25, 26. I think that this is a bowling tournament, is that right? And then we had a number of occasions, including going to tailgating, and every Friday, a very, very rewarding presentation organized by, we faculty are invited, but this is organized by our students. This is open to everyone, and we appreciate the sponsorship that we have from our geotechnical community. But I would like to start by recognizing our foundational sponsor. And for that, I'm going to invite Talia Travasaro to give us a few words and to welcome you to this 2026 Reese Lecture. Talia.
Hi, good afternoon, good evening, everyone. I think it's my third or fourth time being here on this podium, giving this welcome or a similar welcome, so I'm starting to get the knack of it. But I'm really excited to be here amongst this group today, and I welcome you all to this distinguished lecture series in honor of Professor Lymon Reese and his enduring legacy in the field of geotechnical and foundation engineering. FHWA has been the sponsor of this event for more than a couple of decades, so more than I can remember. And anyone would care to guess why? So it's obviously because UT Austin and FHWA are both headquartered in Texas. Okay, just a joke, not sure it was well delivered, but in addition to that, really the main reason is an alignment in philosophy. So for those of you who are not familiar with FHWA, the company, our main mission is to help our clients best manage ground-related risks to achieve better project performance. And we do that by acquiring high-quality geodata, different types of geodata, geotechnical, geophysical. We may not be as good as Professor Brady Cox or Ken Stokey, but we can claim third best, so the bronze medal we can claim. integrating this geodata into robust ground models. We also do foundation testing to reduce uncertainty in the soil structure interaction. So we aim to reduce uncertainty in the ground conditions and the behavior of a soil structure system to ultimately increase or enable confident engineering. And this is where we connect very much with Professor Reese, who really had a foundational change in the understanding of the profession or a fundamental change in the understanding of the profession around soil structure interaction, essentially translating field measurements to impactful and actionable engineering insights. And so in this particular occasion, it is especially fitting that Professor Santamarina is delivering the Reese lecture, as his work really extends the legacy of Professor Reese's work and enriches it, enhances it by looking more, bringing in the element of grain size, physics and interactions, and multi-physics problems into foundation performance and offshore engineering. And so I'm very much looking to your insightful presentation, and please join me in welcoming Dr. Santamarina for this event.
Thank you, Talia, very much. And following on the leadership of FHWA, we're so privileged to have additional sponsors, and this started reasonably recently, and we're so pleased to announce our gold sponsors for this year. Thank you, Ensoft. You have been here with us for so long. Thank you, Geo-Syntec Consultants. Thank you, Keller. Thank you, Terracon. In addition to that, we also are so proud to have NGO, Haley Aldrich, Delve, Newfields, and BGC as silver sponsors. And you know that now we have just finished the Careers Expo. Now we're having the very important lecture. Then we're going to have a reception. But in addition to that, tomorrow we have the very traditional Lymon Reese Memorial Golf Tournament, for which we also count with gold and silver sponsors to give them access to our students that are going to be participating in this event as well, under the leadership of Professor Elmotar. We welcome everyone here, whether you donate or not. But if you want to donate, we can make it easy for you. And actually, we have many opportunities. We have a fund in the name of Professor Reese, and fund in the name of Professor Olson. And this new fund that we call it GeoFuture Pathways, and we're going to tell you a little bit more about it, is integrated with this lecture and the donations that you make to support this Reese lecture. So if you want to donate, we welcome you. And talking about that, and part of the activities that we have been doing to support the outreach of our students, let me tell you about, actually, Professor Clara Saracho is going to tell you all about it.
You can. So this is, hello everyone. Welcome to UT, and thanks for coming to today's lecture and also for coming yesterday. I think it's been very, very vibrant 2 days for all of us and for our group. And kind of trying to sponsor the younger generations. This is kind of what this is about. So last year, the Geotech group, we decided that we wanted to encourage undergraduate students to get exposure to geotech earlier on. And the reason for that is that when we get them to our classes, we only get them as juniors, so third-year students already. So by that time, most of them have already decided they want to do structures. So in order to kind of get them interested in geotech and hopefully retain them as well within our geotech group, we started the Undergraduate Research Fellowship. And this is an initiative that I'm personally very passionate about. It's something that I proposed within the group, and it's great. I always have undergrads in my group, and I feel they bring this kind of very young energy. So I told the other faculty, you should also have undergrads in your group. And that's how we came up with this initiative. So it's really targeted at first and second year undergraduate students. So they've done between 1 and 3 semesters at UT. And the idea is that we have between 3 and 5 undergraduate researchers, so that they kind of start as a cohort almost, and they can learn of each other, but also feel that they're not alone within the geotech group. And the way it works is that each undergraduate is directly partnered with the geotechnical faculty. And then that geotechnical faculty kind of takes them under their umbrella and mentors them for the semester. But equally, they're also encouraged to attend our GI seminars. And some groups also attend the group meetings, for example. So they really get an insight, or hopefully get an understanding of what a career in geotech might look like, whether that's purely more academic, going into grad school, for example, so talking with our grad students and understanding what going into grad school might look like for them, or if they decide to go into industry also, by coming to our GI seminars, they can get exposure to practitioners, right, in the field. So they really get embedded within the group. And last year we had, and I'm going to ask if I invited all the undergrads to join today as well. So if you're in the audience, please stand up when I say your name. But last year we had 5 undergraduate researchers, Valerie Bedoya, who worked with Professor Raji, and they looked at analyzing mean period of earthquake motions in West Texas. Julia Gankaiko, who worked with me, and she looked at hydrogel bioreactors for the characterization of calcium carbonate. Pedro Guzman, who worked with Professor Zomberg on moisture monitoring of infiltration columns. Jim Lee, who worked with Professor Kumar on Gaussian splatting and robotics control. And Jennifer, I'm going to get this wrong, and I'm sorry, Jennifer, Magbagbeola, who worked with Professor Al-Mokhtar on mechanical evaluation of Portland limestone cement. If any of you are in the audience, I think they were, because I did see some of them. Thank you for doing research with us, and I think some of you have even carried on beyond that, so that's very nice to see. So with that, we continued this program this year, and this year we've awarded 3 undergraduate research fellowships. Again, if you're in the audience, please stand up. So this is Serena Sharma, who will work with Professor Raji, Hirva Parekh, who will work with me, and Justin Pollack, who will work with Professor Al-Mokhtar. And they're here. Thank you very much. And congratulations. Yeah, congratulations on this award, and we look forward to having you in our group in the following semester. So this is... there was a slide. So this was sponsored by the GeoFrontiers Pathways program. So that's one of the initiatives, for example, that if you donate into that program, that's kind of what we're using the money for. So it's really to encourage the retention of undergrads, and that's one of the ways. The other initiative that we have, it's geared towards our graduate students. And this is the Olson Award. And this is an award that we started, I might get this wrong, but I think around 2020 now, more or less. And it's really an award for graduate students, and it recognizes different criteria. One of them is, of course, excellence in their coursework and in their research, so excellence in their academic pursuit, so to speak. But also something that as faculty look for as well is their contribution to geotech, right, at the graduate level. And that includes participating in GI, but also can include, for example, participating in the courses and creating a community for our graduate students. And the last one is kind of also embodying that practical, that curiosity that I think really was very characteristic of Professor Olson. So that's also something that we look for in our graduate students, and that we give these awards to the graduate student. So without further ado, so this year our Olson Award goes to Miles. Congratulations. And I had Miles in my class, and I can speak for his unwavering curiosity. Like, it's really something that I remember for everything I talked about. He would always have a question, and what I liked is that those questions were like super thoughtful. You know, you could tell that he was kind of listening carefully, and he was like, well, what about if this happened? And I have to say, sometimes he asks me things, I'm like, you know, I have to think about this, because this is a good question. So, congratulations, Miles.
Thank you, Alexandra. And I understand that we have several members in the audience that belong to the Reese family, and we always welcome you so much. And we would like for you to rise, and we would like to recognize you. And to tell you a few words about Professor Reese, I would like to invite Professor Raji to let you know about a few of the many things that he has accomplished.
Thanks, Jorge. I always relish this opportunity each year to say a few words about Lymon. Most of us know a lot of his technical contributions, but not about his personal background. And just from a personal perspective, he was well retired when I joined the faculty in 1998. But when I took on the undergraduate foundations class, he took an interest in meeting with me and taking the students out for some field trips. And so I got to see some of that firsthand, which was great. So Lymon is from Arkansas, and they moved around quite a bit early on, but he came from modest means. His father worked in the timber industry, and at some point they lived in a rail car, which was with a small attached building. So he really came from modest means. And then the Great Depression happened, and his father gets sick. And so he really had to take it on his own to help the family and work and make money to make sure that they could make it through the Great Depression. It was also, interestingly, at that same time that he became a caddy at the Abilene Country Club, and that's where his lifelong love of golf began. And that's why we are so excited to always host the Reese Golf Tournament along with this lecture today. Then World War II came, and so he volunteered and was part of the U.S. Naval Construction Battalions known as the Seabees. And so he contributed to our nation in that way. And he began, finally, his academic career as a freshman at Rice University at the ripe old age of 29. Think about that, 29 years old. For those of you who sometimes are like, what am I doing with my life? And you're 23, you can figure it out anytime. So he started at Rice, but he finished at UT. So at some point he realized the more flexibility of the program at Texas is what he enjoyed. So he came to the University of Texas. He ultimately got a master's degree, also then went to Berkeley and got a PhD with Harry Seed, but not doing earthquake engineering. It was the 50s, and so Harry Seed had not quite gone down the earthquake route. But then he began his long and prestigious career at the University of Texas. He was elected to the National Academy of Engineering in 1975. He was the Terzaghi Lecturer in 1983. So many awards, but we all know that his contributions all were around deep foundation design and performance. And many of those approaches, analyses that he developed decades ago are foundational. That was not an intended joke. The foundation of the approaches that we use today. He retired in 1988, but his technical work did not end there. He started NSOFT. You saw NSOFT as one of our main sponsors, and as well as Lymon C. Reese and Associates. And so even to this day, his legacy lives on through those companies. So we are so excited to have you here, and we're excited to, again, as every year, celebrate Lymon Reese and what he meant to the program here at the University of Texas. Thank you.
Okay, so it is my honor to introduce the 2026 Reese Lecturer, and this is Dr. Carlos Santamarina. You may have noticed that Dr. Santamarina and I speak somehow similarly. And now, it is not a coincidence, but let me tell you typically when I travel abroad, they ask me, your accent, where are you from? From Texas. So, that makes sense. So just so you know, I've been perfecting my Texas accent for over 20 years now. So welcome, Carlos, as a new Texan. But it turns out, not yet, it turns out that Carlos and I were born at a very similar neighborhood. Both of us, not only from Argentina, but from Cordoba, Argentina. Same city, and we went to the same university. So that explains it a little bit better why we may sound similarly. So Dr. Santamarina was born in Cordoba, Argentina, and soon after graduating in 1982, he went to Maryland, University of Maryland, to get a master's degree in the United States. It was 1984, and I happened to be at the University of Cordoba, and pretty much in a program that may sound something like what Professor Alexandra mentioned. So some of those initiatives to introduce undergrad students to the beauty of research. And I was with my mentor, and they said, hey, we're going to leave the lab, stop working so much. We're going to go and visit Carlos. Carlos. He was not Dr. Santamarina, it was just Carlos. Where is he? Oh, just nearby. So what is going to be there? Coffee and facturas. So, okay, here we went. And I had the opportunity to meet Professor Carlos Santamarina when I was a young undergrad student, and he was just still not a master's student, engineer, an engineer with a master's degree. Life continued, and now Dr. Santamarina did his PhD after his master's in Maryland, his PhD in Purdue. And Cordoba, Maryland, Purdue, that was just the beginning. It is quite a journey. And then he took on a position at New York University, followed by a position at the University of Waterloo, where I understand that your passion for energy started. And then in 1996, he took a position at the Georgia Institute of Technology, Georgia Tech. That was not it. In 2015, Carlos went to KAUST in Saudi Arabia, where he continued to work in new frontiers in energy, geoenergy, among other different fundamental topics. And finally, in what I understand was the most difficult interview that he ever had, he came back to Georgia Tech, now as the Wayne Clough professor in Georgia Tech. He's not strange to many lectures. He gave the Terzaghi lecture, he gave a SSMGE honor lecture, the Bishop lecture, the Casagrande lecture, very recently the Cross USA lecture from the Geo-Institute. And his achievements are amazing, and you're going to see a taste of them very, very soon. But I would like to think of Carlos as I was going to say a meditator, a thinker, always trying to answer fundamental reasons on why things behave the way that they do, very often geotechnical aspects. You may be wondering, what is this video? And these are clips from a presentation, a talk that Dr. Santamarina gave on the influence on academic success, on the virtues such as greed and resilience and mentorship, and how that may influence, and this was geared towards graduate students and faculty, and young faculty, and how these impact success and potentially satisfaction. I think that his thesis was something like, some individuals excel so much with their grit, which, by the way, grit is not an easy to translate term. It's perseverance, but it's perseverance with being able to persevere in face of adversity. So it is a quite unique term. But his thesis was that some people have such an exceptional grit that by sharing that grit with others, they catalyze the greed on the people that work with them. And Professor Santamarina has touched so many people, including some people down there in 1984, back in the days in Cordoba. So it is so wonderful that we will have now the opportunity to talk about the greed of Professor Santamarina, but with another person that is has a particularly exceptional greed, as it is Dr. Lymon Reese. Carlos.
I have never had such a generous introduction. Sincerely, thank you so much. I'm very grateful, but I'm also, it's an honor to be here. I'm so touched by the opportunity to be here sharing this afternoon with you. You know, I have come to realize that technical fields don't fade, don't die because we run out of fun questions. They fade because we stop asking questions that are relevant to society. And so from that point of view, Lymon Reese really addressed important questions, and he answered them, and he moved our field forward. And so we have already heard from Ellen the highlights of his life. I want to say a couple of things that resonate with me. He met his wife at church, so did I. The first child was born a year later, so was mine. And the church is still there. And I was visiting yesterday, and so all the other things were highlighted. The fact that he worked a lot in the offshore industry and that he was highly recognized for his contributions to that field is also an important point that I will come back to it. And in so doing, his work really advanced many different aspects of the deep foundation systems, and I will try to pretty much piggyback on some of his contributions along the presentation today. So these are the contents. I will say something about offshore foundations, slurry construction that he really mastered, pile soil interaction, repetitive loads, and I will say something about corrosion towards the end. So this is the first one, the offshore foundations. That is really a seminal paper, his 1961 paper at the International Conference in Paris. Please take a look at that paper. It's really a wonderful one. And there were simple solutions for the case where the stiffness was constant with depth, but he recognized that that was really not realistic. And so he generalized the solution for the cases where that was not the case, but he needed to use computers, and so he did. He used this one, an IBM 650. It was a magnetic drum spinning at very high speed, and it had a decimal notation, and I think that probably that was the only computer ever built like that. And that is the one he used, and because we didn't have access to those computers, he created all these monograms, etc., that in industry they are still being very useful. I will take just a small topic in the offshore foundations, and I will talk about sediment properties. So coastal geotech is really a frontier for us in our community. Look, folks, 30%, 40% of the US population is in coastal areas. And by the way, that percentage is pretty much the same around the world. And coastal is really a challenging space, and it's going to become more challenging with sea level rise and saltwater intrusion, etc. Imagine the cost to New Orleans, to Miami, to South Texas, to New York. I see Ed here, and he knows that firsthand. This will be huge in the years to come. We are talking about 30 more centimeters by the 2050, and by the end of the century, probably a meter, plus or minus 20 centimeters. These are big numbers. And the number of people that will be affected, Katrina was a 30-foot, 10-meter surge. It's not the wind that caused the damage in Katrina. It was the water advancing and floating all the casinos out of the offshore, made them onshore. But even with a much lower situation, with a sea level rise combined with climate event of 3 meters, 10 feet, 99% of today's homes in 252 coastal towns will be submerged in the US. The cost of this will be dramatic, and so we have to ask, what are the properties that we need? And I like soil behavior, so that is where I'm hanging myself from Lymon Reese at this point. But many of the sediments that reach the coastal areas and the offshore are indeed transported, like we have seen in onshore. Look at the wind dust coming on the Red Sea, or the volcano blowing up in southern Chile, going all the way across Patagonia in Argentina, or the Amazon River forming a wonderful delta. So these are terrigenous sediments that get transported and sedimented. But offshore, there are some unique formations that are interesting to recognize. First of all, there is lots of bioactivity. The diatoms, the foraminifera, and I had to remove a slice. I had lots of pretty pictures, but and all the shells and all the formation of the carbonates, the essential formation of the carbonates. These are going to give unique properties to our offshore materials. And here is Billy, who was working on the sediments offshore North Carolina. And you think of Ariake clays in Japan and around the world. These are going to be very unique materials. Foraminifera diatoms are the culprit in that case. But look at this one. Here we have the Gulf began opening, let's say 300, 400 million years ago. Until that point, big deposits of salts have formed. But the salt is not pure salt. It's not like in the Great Lakes. And so it has layers of wind-blown sediments within it. And so then at some point when it opens up and then we see Africa moving away from us and it got flooded, then the salt is meant to begin dissolving. But as it dissolves, the non-soluble grains remain behind, and that is what you see here, is a dissolution of salt and sand, and with maintaining a low concentration at the top, the front begins advancing, but as it advances, now this becomes a self-armoring layer. It takes longer and longer for diffusion to take place. But all the salts that form the diapirs, etc., that traps the oil beneath or within in the Gulf of Mexico this is the origin. And these are unique sediments that you're going to encounter beneath the Mississippi sediments. Now, in many cases, there are hydrothermal vents, and now we are talking about supercritical water if you're in the deep geothermal. Well, supercritical water is coming and it has the ability to dissolve the silts, the silicas, and then they come and precipitate. And they precipitate in the water column. And the weirdest sediments begin forming. And if you thought that Mexico City soils are weird, they're an order of magnitude weirder. And with properties that are really out of scale. But regardless of the formation history that we need to recognize if we're going to move in the offshore coastal regions, it is important to recognize that some of the things that we have learned in our community throughout the last century still remain. Grain size distribution is critical. The partition between coarse and fines is critical. Please don't use the word cohesive and cohesionless. That's sinful. So between coarse and fine, that is critical. For the coarse, grain size distribution, particle shape. For the fines, it's all about how it reacts with the pore fluids. What happens if there is a brine front or a low concentration front and the saltwater intrusion? And if you run 3 liquid limits, with brine, with deionized water, and with kerosene or decane, you will gain an amazing amount of information about the behavior of the fines. And it could also affect if you have a sewer leakage, etc. This is a very good way to test it. And by the time you bring them all together, it's all about, are there enough fines to fill in the voids in the course? And whether it will be course control, the fines plug the holes, and now the skeleton is still course control, but I think that this is a very smart pointer. Let me see. Okay, this was supposed to, okay, there it is. In this case, now the fines are plugging the holes. Stiffness and strength is controlled by the cores, but the fines are controlling permeability. Changed 6 orders of magnitude by now. And by then, the cores are beginning to float in the fines, and it becomes fines control. This is the essence of soil classification. There are few upgrades to the unified soil classification. Please take a look. We are doing much better today, 100 years or 60 years after Casagrande, 80 years after Casagrande. So now something interesting happens when it is offshore. The sediments form, and there is no capillary action. Everything is about burial and self-weight. And so the question is, how loose could they pack? And if it is a sand, it's going to be somewhere between Emax and Emin. But if it is, as it gets finer and finer, the void ratio gets very large. Those hydrothermal precipitates that I was talking about, they have void ratio approaching 100, and they are stable. 99% of it is water. It's not too far away from Mexico City. 90% is water, but in this case, 99%, and they are stable. And we totally miss them when we put a piston sampler. It just goes through. And so that is not a way to study them. And so this is what we are going to call the asymptotic void ratio at 0 effective stress. It does exist. There is an asymptote. And now I can use those asymptotic void ratios and estimate the pore size distribution and see if there was an interface, if it gets drying, how much suction it could mobilize. For a sand, not too much. That is 40 centimeters of water head. But as you go into the finer materials, and this would be the case of a kaolin is somewhere 10 meters squared per gram, but if you're here, you're already 200 kilopascals. You are 20 meters of water in terms of suction. So that soil is beginning to get squeezed. 20 meters of water is 30 feet, a foot is a floor. It's like having a 60-floor building on top. That is the suction that soil experiences, and it gets much, much worse when you go into the elites and the Montmorillonites. I don't think that we have any normally consolidated soil onshore. But there are normally consolidated soils offshore. Of course, diagenesis kicks in. So now that we recognize that there is no suction, so what is the evolution of the self-burial, the evolution of effective stress? And as it begins piling up on top of each other, it squeezes the lower layers. So how does effective stress, how does stiffness, shear wave velocity? I put a few slides here for Ken's talk. It's a pity that he isn't here, but we'll send it to him. And so, well, there is a very little mathematics here, but the increase on effective stress across a layer is the weight of that layer, and the weight of that layer, the buoyant weight of that layer, is related to the void ratio, and the void ratio is related to the effective stress. A classical differential equation. But in order to solve it, we need to know how the void ratio changes with effective stress. And my goodness, we've been using Terzaghi too much. Nothing is linear. It's just in a narrow range. You can fit a linear thing to anything, right? But it's not. This is a true behavior of soils, folks. It's an exponential decay. It looks almost like, remember Boyle and Marriott's law when you squeeze a gas? We're just squeezing particles. But that's the true behavior. Of course, when you put it in semi-log scale, it looks like that. and then we begin fitting with 1 line, 2 lines, 3 lines for unloading. But that's not real. This is real, and this is more or less a behavior of a soil. And if it has some cementation, then it gets a little bit, but the effect is not so pronounced. This is the true behavior. So now we can begin predicting, with that equation and the self-burial, we can predicting how the effective stress evolves with depth. This drawing is biasing because I put it in log scale here, because otherwise I cannot capture the whole data set. But this is how effective stress increases with depth. This is the way porosity decreases with depth. And these are soils from all over the world compiled. And these boundary lines are the ones that I described earlier from soils that we have published, that we as a community, way before I was born. And so they work really well. That is the behavior of soils offshore. And now, this is the way the shear wave velocity increases with effective stress. Stokes worked for decades. And so this alpha factor and beta exponent are related one to each other, by the way. And so it's not that we have 2 degrees of freedom and they depend on soils. So somewhere Mexico City is here, remolding Mexico City is here. These are sands, silts, sands, etc. Quite predictive. Now I can use this equation and the effective stress that I computed before to tell you what the shear wave velocity is. And this is data from all over the world. And we are just concatenating calculations from the previous slides moving forward. And we're predicting very well for the different soils. And if I know the shear wave velocity, and I know the bulk modulus of water, and then this is a simple equation, it's called Bio-Gassman, I can predict the P wave velocity, and I get the P wave velocities quite well, which means something very interesting. Now I can take a sub-atom profiler, or I can analyze a marine seismics, and from the data I can begin predicting what soil types I have. And then from there, you move through the whole sequence of events. So it's a very powerful way of characterizing our offshore sediments. Now, the story, as we move forward, will need the hydraulic conductivity, so I'm going to say something about hydraulic conductivity. At the beginning, I said, well, void ratio is quite irrelevant. That is a very bad thought. It is a secondary parameter, or porosity, but it is an important one. This is sand, high permeability, low range in void ratios, but as we move into the silts and sand and clays, this is a bentonite, we see that the permeability is quite related to porosity, and if I look at the intersection at void ratio 1, that is the permeability at void ratio 1 is directly related to the specific surface. Specific surface is a very good parameter to measure, and it's very easy. So if you ever order somebody to do a liquid limit, you have to request that they do a specific surface because it's very informative. And so now we know how compressibility works, how permeability evolves, and we will be able to do a few things. But this is, once again, going back to Ken Stokes, it is great to recover sediments and to measure the velocity, but the problem is that recovering sediments is quite a tortuous experience for the sediment. All the state of stress gets released, altered. And if you are offshore, when there is high pressure in the water, gases are in solution, that when you bring them up, it's like opening a Coca-Cola can, all the bubbles come out. And now you have chocolate mousse, you don't have a sediment anymore. And so what can you infer from that? And so that gets very tricky. But this is data primarily from Ken on the effect of the shear wave velocity that you measure in the lab compared to the field for sandy soils and clay soils. Yes, there is pronounced disturbance, so we have to handle that data carefully. And so we want to measure in situ, but let's say that we want to measure with a cone. Now think at 1,000 meters of water, you have 10 megapascal of pressure. Think of that pressure pushing the cone. You're not going to measure the soft sediments. This is controlled by that huge force. So there are possibilities now that you can develop a cone where you compensate what the cone measures with the external water pressure, and you just use a differential pressure transducer. Today we're looking at differential pressure transducers with shad. Indeed, they are extremely sensitive. And even at deep water, we can measure the penetration resistance of very soft sediments. So there are great opportunities coming up offshore for our industry, for our ability to characterize, etc. But there are differences. Those soils have not been exposed to capillary action. Let's talk about slurry construction. Lymon Reese is the one who really pushed the boundary on that. And so this is coming from his Terzaghi lecture, that sketch on drill shafts. And he gave us wonderful guidelines and recommendations. He identified 3 problems. One is that the yield strength of the slurry increases with time. This is thixotropy. The second one is that as that slurry pushes against the boundaries to hold the borehole open, the water goes through, the grains remain, so there is filtration taking place, and this is going to form a cake. The third one is that some of the slurry actually may penetrate the formation and will alter the properties. For drill shafts, this is not an important issue, as they recognize, insignificant for load transfer, but for other applications, including stone columns or oil production, this is critical. And so let's explore this a little bit. And by the way, if you keep reading the manual, this is from the O'Neill and Reese manual, there are lots of wonderful jewels of recommendation. And one of them, they keep insisting on 4 hours. Agitate, if you're going to wait more than 4 hours, you have to agitate the mud. And if the mud is thicker than 2.5 centimeters, you have to go back and re-ream the excavation before you place the concrete. Wonderful explanations, but I wonder where they got the numbers from. These are very empirically driven. Let's see if we can make sense of them. And so this is the model that I would like you to have in mind. On the one hand, you have the slurry. This is the formation, let's say sandy formation, these holes, or what this is, these grains. And this is where some of the mud invades at the beginning, and the cake forms. And that cake is critical. That's the one that holds the borehole open. That's critical. And that is the same as a French press. You have all the grains in there floating in suspension, and you begin pushing, and now the boundary is moving. In this case, we'd like to think of the borehole wall as a static, but it's exactly the same. So next time you make coffee, get inspired. There is something there. By the way, we always process the data from odometer tests, let's say Terzaghi theory. The constraint modulus, the AV divided 1 plus E, is the constraint modulus, constant. Permeability, constant. Folks, we already showed that constraint modulus depends on stiffness, and the permeability depends on void ratio. The void ratio is changing, and it changes faster at the boundaries than in the middle. So this is a very complex problem. For small changes, well, we assume something, right? But when things are going to change so much as during the mud cake formation, we can't. And we have to take a more comprehensive look. By the way, that we heard from Drenevich yesterday, this is a wonderful sequence. There was a paper there. Mesri got involved. There were lovely discussions. I haven't figured it out. I'm sure that Olson was involved too on this one. But anyway, this is where I would like to continue this story. Remember the Macondo well. The Macondo well was an amazing drilling experiment. They were in 1,500 meters of water. Probably you're more used to feet. I apologize, multiply by 3, the 4,500 feet of water. And then they went down like 4,000 meters into the sediment. This was a deep well in the Gulf of Mexico, using this rig, built in South Korea, beautiful deep water horizon, $1 billion. It was pretty new, $1 billion. Doing this hole probably was like a $200 million test, and it blew up. And the environmental consequences were quite pronounced, as you may remember, and the economic consequences for BP were terrible. Probably at least $100 billion at the end. What happened? It was all about mud formation, cake, displacement by the cement grout, the same way we do in TREMI operations, but now happening in a borehole at great depth. And we would like to explore that a little bit better. And so we take the equations that we had mentioned before. Remember the compression equation of sediments and the permeability as a power function. We curve fit data to the extent that is available. That is the void ratio at zero effective stress that we were talking about. And now, with Lagrangian formulation, etc., I begin predicting how this is going to drain and squeeze itself and form the cake. And so the results are as follows. Within 1 minute, this is the void ratio of the slurry, let's say 35. Within 1 minute, you have already formed a significant cake, probably 3 or 4 millimeters in diameter, in thickness. As time passes by, we're approaching the 4 hours from O'Neill and Reese. As time passes by, the cake has become fairly thick. Now it's 12 millimeters or so. And the void ratio near the wall goes to the effective stress very fast because it drains right away. And so that is the evolution of the cake. In the meantime, and this is data from Shadi, the viscosity, because of thixotropy, the viscosity is increasing. And if we use more or less this power function to feed their data, within 4 hours, the viscosity, the yield stress of the slurry has increased by probably 3 times. So it gets thicker. So you do need to re-agitate the formation. Now, when we put all that together, now you have to think, will the grout, the cement, the concrete that you're placing in the TREMI operation or the grout in the borehole be able to displace the cake and the mud? And now you can think of the yield stress, or let's say 0.2 sigma prime from more Coulomb, and this one is from the test by Shadi, and then you can see what will you be able to displace or not, but you will leave cake behind. And the question is, how will that react with the cement? And the cement will contract, and the cake will take some of the excess calcium ions and contract further, and are you going to have a path for gas to make a gas bubble that will reach the drill rig at the top, in this case? And by the way, with respect to invasion, and Shadi, there is your data too, another data set. We've run several tests here with syringes and with odometers, how far it invades, and in general, the depth of inversion related to D10, which controls the pore size, is directly related to the pressure that you apply with respect to the yield stress by a factor of 0.1, 0.6, somewhere there. This is a very complex phenomenon because as the slurry is invading, it's draining out the water and its strength is increasing. So we think that we know the strength of the slurry, but that's not the front that is invading. So it gets very complex. As you can see, the data has the plus or minus half an order of magnitude uncertainty. Pile-soil interaction. This comes from Lymon Reese's Federal Highway amazing book, but I'm from the Casagrande lecture, but one thing I didn't fully appreciate before I started preparing for this talk is that he did part of the contributions for the PY curves, the laterally loaded ones that probably we are more familiar with, but he also did it for the QZ, in other words, the vertical actually loaded piles. And I will come back to that, and these are the classical sketches of pile-soil interaction. So look at this. This comes actually from the paper with Sid. The paper actually is in 1955, but it appears to be published twice, again in 57. So if you see that little uncertainty there, but this is the data that they had in the paper. Look at the quality of that data. It's in the Baymad. All these points are from strain gauges. They open the steel pipe, they open it, they glue the strain gauges, and they put it back together, and they push it. The data is exceptional. And then they did a mathematical formulation, and you have the classical formulation for the tau Z or QZ curves. And by the way, one more detail. If you look at the acknowledgements in the paper, they acknowledge Carl Smith and Ray Clough. Carl Smith, famous in pavement discipline, he's the one who went on to the mechanistic design of pavements. Finally, we move out of CBR, but not everywhere. And Ray Clough is not our Wayne Clough. This Ray Clough is the one who invented finite elements. What a time at Berkeley. What an amazing time. So now I go back to use his formulation for problems of wells, because I really think that the energy geotech has an amazing opportunities for our community. And so not only that we had that multimedia, multi-layer system, we also have all the actual loads that go on the pile and the shear loads and thermal loads, etc. I will give some examples. So this is a case. This is a case at Nankai Trough production that they were trying to produce gas from methane hydrates. This is like 2,000 meters of water, and the hydrates were 160 meters below the sediment level, and so they put a well, and they began depressurizing to produce the methane. Within a day or two, the whole thing clogged and then collapsed, and they couldn't understand why. So here we try the Reese's QZ curves. And you begin doing pile-soil interaction, recognizing now this is not downdrag, it's not the sediment consolidating at the top, this is the sediment consolidating beneath the pile or at the lower level of the pile. So this layer will squeeze, and now instead of downdrag, you have the whole well hanging from the sediment above. And it is all dependent on how stiff the lower level will be, how much is the peak load that will be mobilized. But furthermore, so this is what this plot tells you. So then we wanted more degrees of freedom, so we moved on to finite elements to control the situation better, and we got the same thing, but with more details. And so look at this. This is intention. But I don't think that it failed intention. I think that this is the yield capacity of the well. I think that we just longitudinally buckle the pile, but furthermore, in the lower part, you have what they are called the screens to hold the sand from coming in and to be able to withdraw the gas, and I think that they just crushed the heck out of it. And so now that we're there, we can play a little bit more with low soil load transfer effects. And for example, we put a slip joint. Imagine a telescopic well that can accommodate displacements at the top. So we kill the tension a little bit, but most importantly, we put a telescopic contractile end, and that decreases the huge load that picks up at the bottom. So we can engineer better wells if we understand soil-pile interaction, thanks to Lymon Reese. The next one is that in several parts of his publications, they highlight the importance of repetitive loads. Repetitive lateral loads, and in his quote in a paper by Broms there, a classical paper by Broms, repetitive lateral loads gradually decreasing the shaft resistance. But he also talks about cycles in moisture, cycles in pressure, and he made beautiful distinctions between one-way versus two-way action in cyclic load. So in cyclic load, you could put compression and tension, let's say the external piles of a building, but you could only go down and come back to a neutral value and come down, and it gives you completely different behavior, beautifully recognized by Reese. And so, building on that, these are some of the caissons, and these are laterally loaded piles, and you think of how element A and B are being loaded and moving towards and away from the failure line. What happens if it is vertically, executing primarily shear? What happens if the pore pressure is going up and down? And at the tip, or a shallow foundation, moving close to a K-knot line or something of that kind. All these systems are going to give us different accumulation of the formations. Typically in our literature, we tend to think that the first cycles matter. Look at your driveway and how much it cracks, and you know that it's more than a few cycles. And so things keep accumulating way beyond a few cycles. And yesterday we were talking, and Ricardo Dobri was sending us a video, and Ricardo talked about the elastic and volumetric threshold strain, beautiful work from the 80s. We can continue accumulating the formations beyond Vucetich and Dobri's threshold strain. And we have to wonder how could that be possible. But that is the challenge of repetitive loads. And so take a look at the sand. We tend to think of sands very stiff, but you can put sand in an odometer and measure, and you go up and down, and you begin accumulating. This is 10,000 cycles. You begin accumulating quite a lot of the formation, and this is for a loose sand. For a denser sand, this 86% relative density, you still have significant accumulation. And if I stretch it in time, I see that they are all approaching to some asymptotic value. There is a terminal void ratio, and that reminds me of the Casagrande type of thoughts. There is a terminal void ratio for repetitive load, and nothing to do with liquefaction. And in fact, you can fit it with this equation. It fits very well, as you can see the red line. And when you go to I equal infinite, it gives you the terminal void ratio as a fitting parameter. So it's very robust, and there is under zero lateral strain, or under pure volumetric strain, there is a terminal void ratio. But what happens in shear? Well, this is now in a simple shear device, and we apply a certain static shear and then an oscillating shear, and we want to see, is it going to continue shearing? We already know that the volume will go to an asymptote, but what will happen with the shear accumulation? In this case, the static shear gives you the idea that you are on a slope, for example. Wonderful cases by Ron Scott. So if the amount of shear is not too much, this doesn't mean anything, everything is relative, but you're far away from failure, it goes to an asymptote. But when the amount of shear is more pronounced, now you have a monotonic static shear of 150, you add 50, you're bringing it close to the Coulomb failure. Now you continuously accumulate shear. It doesn't go to an asymptote. Shear keeps accumulating, that's called ratcheting. And so this is the concept of ratchet coming from Leonardo, the idea of a ratchet, and that is what we are doing to soils. Now, for peace of mind, let me tell you something. If you are not close to failure, probably ratcheting is not going to be a problem for you. And, but if you are close to failure, and this is, imagine this is the failure, this is normalized by the failure load. By the time you are approaching 80% of the failure load, you really have to begin thinking carefully about the possibility of shear accumulation. We don't handle monotonic loading very well, and I'm telling you, we better begin paying more attention to repetitive loads. They are multiphysics of all kinds, and they are affecting the long-term performance of our infrastructure. So from a point of view of, this is a four-dimensional plot. This is tau sigma, and this is a sigma void ratio, and this is the deviatoric strain. So from the point of view of void ratio, it will go to asymptotic value, it cannot vanish. It goes, but from a point of view of shear, it can continue accumulating if you are close to, the peak is close to the failure mode. Now, we are beginning to use our deep foundations as heat exchangers for what we call thermally active piles. There are codes in Europe to do that, and it's not totally catching up in the country. Some universities have demo experiments, but I think that it's going to begin, we're going to move in that direction a little bit more. And so let's do an experiment here. Imagine this rock block that gets heated up, so expands, well, it's hot. Then when it gets cold, it contracts, but it doesn't really contract from the back, it contracts on the front. So the choke blocks fall further down, it hits again, expands further down, and then the choke blocks go down again. Now we have a thermomechanical ratcheting in our retaining wall, in our walls, in our exposed rock masses. And you begin to see them. I'm going to use this pointer, it's amazing. Look, you see that wedge? When the upper wedge hits up, it's going to push. This is not Dick Goodman's toppling. This is thermomechanical ratcheting. This is going to move forwards. And this is going to happen. The good news is that for the heat to penetrate, to have this effect, it's a diffusion process and it takes time. So it won't happen with cold and hot during the day. It does happen with seasonal cycles. Take a look at that one. Where is the other one? Let's see. Now I will need it. There is the other one. That block is also this under the port there in Grand Canyon. This is going to move out. And now I'm paranoid. I go to the mountains and I'm looking for those wedges and I find them everywhere. So keep an eye on that. Please send me pictures. I have a collection. Please do. So let's go back to Lymon Reese. It's a pile. Now we put tubing inside to circulate water so we can store the heat in the summer and pull it back in the winter. And what will it do to the pile? So let's take Reese's QZ method. And you write the formulas and you satisfy equilibrium, compatibility, and all that, and you begin moving things around. This is what the static load is. Before you get scared, this is a fairly extreme case. This is primarily shaft resistant. The shaft carries 70% of the total load, and with a factor of safety 1.25. You know that is not good. You're too close. And so you begin doing it, and now you change the pile-soil interaction, because when you hit the pile, it's going to expand. And then when it cools, now things begin migrating and keep migrating. And the light gray here is the original static load, and it doesn't appear to have moved much between, this is after 50 cycles, but there is accumulation of vertical displacement. It will not affect the ultimate factor of safety, but we have to keep an eye on what happens with the displacements. To aggravate the situation a little bit more, this doesn't consider what happens with the behavior of the soil during heating and cooling, and go back to Mitchell and Campanella and thermomechanical consolidation, etc. So it may get a little bit more complex, but I think that we're overall on the safe side, but there will be deformations involved. This is for Jorge Zomberg. Jorge, these wrinkles of this exposed membrane is because of thermomechanical ratcheting. And by the way, we did the experiment. This is experimental data. A few more thoughts, and this is on corrosion. And O'Neill and Reese made many points about corrosion, particularly for reinforced, for cases with a cage. And so let's take a look. There is plenty of evidence of corrosion. I was visiting Anne Lenmitzer recently, and she had exhumed if you haven't seen her work, it's beautiful, so please take a look. But she had exhumed also some steel piles that she had there, and looking at it, there were quite significant amount of corrosion, so I decided to put something on corrosion in this presentation. Corrosion is a big problem. It's about 3-4% of the GDP. That's a big problem. And globally, it's $2.5 trillion a year. And a significant value, according to their association, a significant value is preventable with existing technologies. By the way, we had lots of projects on this from Aramco. If you have been following the news, Aramco has a big pipeline that goes from Jubail to Yanbu, crossing the kingdom, trying to get the oil out now, avoiding the Strait of Hormuz. Well, we did lots of work on that pipeline, they have similar numbers, $900 million a year, the cost of corrosion, 25% preventable, but the deferred production costs every time they have a failure is 50 times greater. This is a costly problem. And so didn't get stuck here before. Okay, here it is. Just to give you an idea, you can have a few hints here. If it is reddish and orangish, it's because it has plenty of oxygen. By the time it gets dark, it's lacking oxygen. So, and Alexandra, this is you. So let's take a few examples. We ran more than 1,000 tests on this, and some of them were sealed, some of them were not. But you see in this area, this is the message. It's good to have oxygen for typical corrosion. You could have hydrogen-driven corrosion as well. And to have oxygen, you want to have percolating air. And that is what is the message here. It's more important than whether you have deionized water or brine. So we always pay attention to the conductivity, the electrical conductivity. It's not that critical compared to other parameters. And this is the case. And if you look very carefully with the microtomographer that you can resolve the grains, you see this patchy water. This is called patchy water. When it is unsaturated, this is very nasty, because this is what favors the formation of electrochemical cells. And it's all about electrochemistry to some extent. And so that's the reason why the peak of corrosion happens in certain regimes. You want to have water, so you want to be to the right here. It has to be air percolation, you want to be to the left. And if it is patchy, it is really tricky. And remember the soil water characteristic curve. Here we go into the same problem. So depending on your soil structure and the presence of fines, and remember what we were saying about soil classification, that will control. So lots of tests on that. Just pay attention on the fines. Fines is always the nasty one. And one more thing is, we go back to repetitive loads. But in this case, we have repetitive wetting and drying. And when that happens, you're facilitating the migration of air and the migration of the corrosion byproducts. So you prevent passivation, and this becomes trickier. So this is what the data shows, that if there is cyclic for the same period of time, it's much more effective than being dry or saturated. We are promoting transport, and good part of corrosion is transport limited. Once again, you can go into microtomography and you see how the corrosion byproducts begin migrating away from the shim, from the metal body, as corrosion is progressing. Closing thoughts. Lymon Reese really brought together understanding and experience. He pioneered the algorithms for analysis. Really so impressive. His 57 paper, his 61 paper, truly impressive, marked the field. The steel-based construction practices recognize the importance of offshore foundations, something that remains as critical or more nowadays, and highlighted the importance of repetitive actions of multiphysics sources. I wonder, what would he be working today? I should have asked ChatGPT, okay, but I didn't. But what would he be working today? And I don't know, assessment and retrofitting of some of these caissons, and more advances for offshore. Self-sensing, now we are putting sensors everywhere, and what would that tell us? Bio-inspired foundations, the 3 roots that some of you guys have worked on. AI-assisted analysis, Krishna and Ellen, and where is that one going? From the technical point of view, coastal is really a rich space for us. Just keep an eye on how the sediments form. Don't just transport onshore to offshore. There is a different formation history, slurry construction, the mud cake formation and the thixotropy, critical for well completion and drilling. Soil pile interaction, we also saw how important it was, and it's not only the downdrag, there's also swelling effects, in this case, putting the well in tension. Repetitive loads, volumetrically is going to go to an asymptote. The shear is the question. Will it shake down or continue ratcheting? And corrosion is a problem that we are going to face. We have built so much in the time of Lymon Reese, and so much to maintain and retrofit with huge corrosion issues. This has been the work of so many people, and I just put a few names here. If you are interested about source, we are trying to put some videos on the computer. But above all, I'm so grateful to all of you, and to Jorge, and to the inspiration of Lymon Reese. Thank you.
We are going to open to questions. Any questions from the audience? Thank you so much, Carlos, for this outstanding lecture. Questions? Comments? Please.
Is it on?
Yes.
And I would like to point out a couple of things that he had in his drill shaft manual that about the use of drilling slurry and drilling holes in the ground for drill shafts. The reason that contractors want to use drilling slurry, first of all, is for borehole stability, okay? And when the filter cake of a mineral slurry is formed, it's necessary that you have an outward hydraulic gradient flowing from the borehole into the formation in order to get the filter cake to form. And there are situations where this is extremely important in order to get the borehole stable, particularly when you're drilling offshore and you've got a saline groundwater, but you're mixing your drilling fluid with a freshwater in order to get the drilling fluid to for the drilling fluid to have the flocculated clay in the drilling fluid, okay? So you've got to maintain a higher head in the borehole than you do in the surrounding ground. And the way that that is done is by having a piece of casing to raise the free surface of the slurry higher than the surrounding saltwater water table. And that's very important. If you don't have that outward hydraulic gradient, you're not going to form a filter cake no matter what you do. Okay? And then with that with that point made, I just wanted to say one other thing. The purpose of the 4-hour rule about stirring up the slurry and to break down the thickness of the filter cake, that's also to prevent an excessive buildup of sedimented solids on the base of the shaft that would destroy your end bearing. So that's the other reason for that 4-hour rule. But there are certain circumstances where it's okay to leave the slurry in and not stir it up. And that would be the case where you're drilling a very large diameter, deep borehole that you cannot construct in a single work shift, or when people, you don't have labor available for a night shift. What you could do is that you could drill the shaft partway down, undersized on purpose. Drill a foot smaller diameter hole for partway down. Let the slurry stay in the borehole. Don't even bother to clean the suspended solids out. Leave it overnight so the borehole is stable. Then you can come in the next day, complete the borehole to full depth. Then you over-ream to remove all of the filter cake that you would have that could potentially destroy your side resistance and axial load transfer. Then you get the slurry column, remove all the suspended solids, get it down to under 4% suspended solids to prevent the excessive buildup of sediment before the slurry is, before the concrete is placed. And then when you place the concrete with a properly high controlled slump with retarders in the mix, so the first bit of concrete that you place remains fluid all the way to the end of the concrete placement, then you can put your trimming down to the base of the hole, start placing your concrete, push that slug of contaminated concrete and scraped off filter cake up to the surface and get that concrete out and waste it. And then you've got a full borehole full of high quality concrete. So that's the whole purpose of the 4-hour construction rule that was in there in the standard specifications. So,
by the way, I'm not quite sure you heard the name at the beginning, and for the recording, Bill Eisenhower, and so grateful for your comments.
Yeah,
I think that we are in total agreement.
And but things get even more complicated when you use a blended slurry that has both polymer and drilling montmorillonite blended together, because that's a product like the Baroid Quick Gel. That's a product that is trying to get the water loss properties of a mineral slurry combined with the higher effective unit weight properties of a mineral slurry. And those products have their own set of tricks to take care of in construction.
I think that at the beginning, the concept of the gradient in the direction, etc., wasn't so clear. But basically, the slurry has to have the weight to push the water out, but also to push the formation out, right? And so you need to have both. So it's an outward flow that you have to create. In the petroleum industry, this gets very tricky, because if your mud weight is too heavy, that you need in certain locations, and then all of a sudden you cross a layer, now your mud weight may be too heavy and you break the formation and you cause hydraulic fracture. And so these are some of the very tricky things, and you have a narrow window to progress, and it is really a quite fascinating area to work in. Thank you again.
Other comments or questions?
Tim Fox. Now, these are stories that I heard when they did the Harbor Bridge, and they had soft soils. So these were like 10 or 12-foot diameter drill shafts, like 230 feet of penetration. And what they didn't think about is that how long it takes to drill that and how long it takes to put the concrete in that hole. And then they started load testing, and they weren't getting the capacity anywhere, and all of a sudden the project got stopped. In my understanding, this is just discussions from people involved. I'd be interested to know if anybody else heard anything of that, but basically got down to the slurry, and TxDOT had outlawed using polymer slurries. And so my understanding, they got Baroid involved and had to redesign the slurry to deal with this, and they eventually solved the problem. But, obviously a very thick filter cake developed when you're going to drill it. I don't know, a couple days to drill it, a long time to concrete it, So they went after much more than the 4-hour period, Bill.
Yep. By the way, do read the manual. It has all these instructions in detail. It's really quite a wonderful guidance.
Thank you for the comments. One last question? Comment?
Thank you. Thank you for the lecture. You always inspire us to think more deeply and go back to work we've done and rethink it. So, with that spirit, have you looked at the effect of the velocity of the circulation on that filter cake? Because we got very interesting results on what actually is driven by that differential pressure if you also have different circulation velocities.
Yes, and in fact, in many cases, the petroleum industry increases the rate of cement injection to actually play with the viscous drag, also to shave part of that cake. So velocity does come as both in your drilling operation and in your cement job as important parameters for this process. So total agreement.
Very good. And I would like for you to join me to thank Carlos again for a wonderful